Hey guys, for those of you that were in class, you've already seen these two examples on two-dimensional collisions and explosions. For those of you that were absent, you should probably watch this video, and then if you need more, then you can go on to the second part of the video. So what we're learning about is two-dimensional collisions and explosions, okay? And so that's any kind of a thing that looks like this, or maybe two things run into each other going like, sorry, you can't really see that, going like, say, this, okay? And therefore they would fly off this way. You've all seen two-dimensional collisions before, especially if you've, say, played pool ever. So what we're going to learn here is not going to be anything bizarre and outside of your experience. We're just putting math into things that you've seen before in real life. Okay, so the principle here is that momentum is conserved during collisions. However, momentum in the x direction is conserved separately from momentum in the y direction. So thus, when we get a collision here between, say, like this 2 kilogram ball and this 1 kilogram ball, we would not expect, for example, that after the collision, this one goes like down this way, and this one just keeps on going straight forward. Like, that's not the way things happen, right? If you're playing pool and there's a glancing collision, you know one ball is going to go down this way and the other one has to go up that way. The reason we expect to see that is because momentum is conserved separately in the x and y directions. So when you look at this one, it has 0 y momentum. Nothing has y momentum at the start. If this one then ends up with momentum in the negative y direction, that means that after the collision, this one has to have momentum in the positive y direction so that they can still add up to 0. Okay, so mathematically then, the way that you're always going to set this up is break it up into x and y. And just like when we did two-dimensional kinematics, nowhere in the various equations that you write are you just going to plug in this 8 as is. This 8 meters per second for the 1 kilogram object has components, right? It's got an x component and a y component. The x component is going to go in the x momentum equation, and the y component is going to go in the y momentum equation. But nowhere does the raw number, just 8, go into it. Okay, so let's start this. In the x direction, the initial momentum is this one right here. So if you had to put a number to it, it would be 20. Okay, so there we go, 20. All right, on the right side of the equation here, after the collision, the 1 kilogram object has some amount of momentum in the horizontal direction. But I'm not just going to call it M2 V2. Notice I'm saying M2 V2X to indicate that we just want the horizontal component of it. All right, so that would be 1. And then for V2x, it's not just 8. Remember, it's going to be 8 cosine 30, because that would be the horizontal component of this 8. Okay, so that's going to be 6.39, no, 93, 6.93. Oh yeah, and we forgot about something. Up here, right, that's not the only thing that has momentum. Otherwise, 20 does not equal 6.93. That would be all kinds of bad. So this one up here has some amount of momentum, and its momentum I'm going to express as M1 V1 final x. Meaning, when I get my answer, it's going to be just the x component of the 2 kilogram object's velocity after the collision. Okay, and a little bit of math later then, we're going to end up with V1 final x equals 6.54 meters per second. All right, now, what we just got then is this. Here's V1 final, right? 6.54 is just this component of its velocity. To find out what V1 final really is, we need to figure out what this component is, which means that we need to look at the y direction now. this over a little bit. The y direction. Remember, we said momentum's conserved independently along the two axes. So this is our x equation. Right, this one had momentum in the x direction initially. The initial y momentum is nothing. Nothing is moving along this axis initially, so we'll just put 0. All right, after the collision, m1 here, well, let's talk about this one, I guess. This one is moving in the, let's call it the positive direction. So its momentum I'm going to express as m1 v1 final y. And then the other one is moving in the negative direction. So I'm going to put its momentum as along this axis as m2 v2 final y minus because it's headed downwards. All right, and v2 final y is going to be 8 sine 30. So that means v1 final y is 2 meters per second. All right, so that right there is the y component of v1 final. All right, now what would they ask us to do? Because we just did a whole bunch of math here without any real context of a specific question. So the way the question would be given to you would be something like a description of this collision or maybe even a diagram of the collision. And then they would say something like, part A, what is the final velocity of the 2 kilogram object in unit vector notation? All right, well, in unit vector notation, that's what we have, right? There's the I component, there's the J component. So in unit vector notation, we would say V1 final is 6.54 I plus 2 J meters per second. All right, or they might ask for the final velocity as a magnitude and a direction. And if they ask for that, then we've got, a little bit of Pythagorean theorem and a tiny bit of trigonometry ahead of us, right? If we Pythagorize this, right, to find the hypotenuse, we're going to come up with V1 final is 6.84 meters per second. I did that in my head. That's not true. Okay. And the direction is going to be inverse tangent to give us, as it turns out, 17 degrees. All right, so there's all of our answers. All right, there are a few other things they could ask here. I'm not going to work it out because we've done this particular type of question a whole bunch of times, right? If they say, what is the change in kinetic energy of the system, right? How much energy is lost during the collision, something like that. How much energy is turned into heat. You could work that out by, say, finding this initial kinetic energy, finding the kinetic energies of each of the two objects after the collision, okay? Add those up and you'd call that the final kinetic energy, all right? And then final minus initial is going to be the change in kinetic energy. I only mention that because when you plug into 1/2 mv squared for, say, this one, don't plug in either of the components, right? The v in your 1/2 mv squared is the speed, right? It's the magnitude of its velocity. So just be careful not to plug in any components because it's neither of these, but rather the speed. So the hypotenuse there, that's going to determine your change in kinetic energy. All right, let's look at another example. That one was a collision. Here's an explosion. Okay, now if you're looking at an explosion, sometimes the picture looks like this, sometimes it doesn't, right? So the book a lot of the time is going to ask about things like a nucleus that's exploding, right? So you're not going to have 4 kilogram chunks coming off. It's going to be itty-bitty fragments of matter. But regardless, if this is your picture, they should make a certain amount of sense. If I'm, say, standing on let's say a hoverboard, okay, because that can float in any direction. If I throw a bowling ball at the camera, that means I'm going to recoil in this direction. If I then throw a second bowling ball this away, then I'm going to recoil in that direction. If I did both of those things at the same time, then you would expect that I would recoil not exactly this way or that way, but both of those things simultaneously, right? I would go in this direction. And that's what we're seeing here, right? So if this piece gets kicked out that way, this piece gets kicked out this way, then because of conservation of momentum, this fragment is going to have to move up in that direction. Okay. So, but your process for working this out, though, is going to be exactly the same. You would write an x equation. All right. This one has momentum in the x direction. Its momentum is mv24. All right. The horizontal component of this one's momentum is entirely based on how much momentum is there. So we would say it's m3 v3 final x. Okay, and since this is 8 kilograms, horizontally, this fragment's going to move away at 3 meters per second. All right, the y direction, same idea, right? It's got 16 in the negative y direction. So that means this fragment's going to have momentum in the positive y direction. Okay, so its velocity in unit vector notation would end up being 3I plus 2J. All right, so that's not a complicated process, but it does require that you separate x and y from each other. If you don't separate your components, then all kinds of bad things happen. Okay, so good then. Now if I wanted to speed in direction, that's what we did last time. Okay, so I'm not going to bore you with Pythagorizing and that sort of thing. Now, for the work done by the explosion, I'm only asking this because it's an extension/review question, right? And you do need to have review from time to time. Whenever we say work, a lot of people immediately go straight to, oh yeah, force times distance. Got it, Mr. Errico. Right, work equals force times distance. That's, the force is, okay, and you can't do it that way because you don't know anything about the force or the distance. Okay. Rather, you go back to something which is even more basic for work, which is the change in kinetic energy. All right, at this point, it's a little bit of number crunching, right? But if you wanted to know the answer, it actually comes out to be 156 joules. That's based on this one's kinetic energy plus this one's kinetic energy plus this other fragment's kinetic energy. Add all those up, and that has to be the work that was done by the explosion. Okay. If you need more examples or different examples, then you should check out part 2 of this video, in which we deal with more and different examples. All right, I hope that was helpful, and I'll see you in the next video.